Let's go through the exercise then using the 11-step method. Step 1 is your design objective. Now this is specified as life safety, and it's specifically to maintain a clear layer height above the mezzanine. And in this case it's been decided to maintain a 3.5 metre clear layer height above the mezzanine. Usually it's only 2.5 metres for staff, but in this particular circumstance it's to maintain a clear layer height 3.5 metres above the mezzanine, as you can see here. So that was step 1. Now step 2 is to determine your design fire size. Now to determine your fire size in this particular instance, based on the information you were provided, this is the model you should have used. QP equals chi times AS times QF. Now if you'd have put these in, you'd have got QP equals 0.8, which is your chi, times your 9, which is your area of fire, times 625, which would have given you a convective heat output of 4,500 kilowatts. So that's step 2, design fire size. We know that now. Let's work out the mass flow rate of smoke. Step 3. Now we firstly need to establish whether or not it's a simple plume or a complex plume. In this case, the design fire is located in the reservoir where it's going to be extracted. So clearly it's a simple plume. So we know it's a simple plume. Now we know which model to apply. Is it a line plume, corner plume, wall plume, or an axisymmetric plume? Well, in the design stage it was identified that it was an axisymmetric plume because it could have been anywhere inside the atrium, and that will give you the most flow rate of smoke due to the air coming in at different angles. So an axisymmetric plume will give you the maximum amount of smoke. So we know the type of plume, it's an axisymmetric plume. Now we need to know whether it's a near field model or a far field model. And don't forget, if the clear layer height is greater than the longest dimension of the source by 5, it's going to be a far field model. If not, it's a near field model. Now in this case, 5 times the longest dimension of the source, which is 3 metres, is 15. And the clear layer height is 24 metres. Well, clearly this is a far field model. So now you've identified not only is it an axisymmetric plume, it's a far field axisymmetric plume. This is the model we've got to apply to work it out. M smoke equals 0.071 QP to the third times Z minus ZO to the 5/3, where QP is your convective heat output, Z is your clear layer height, and ZO is your starting point for your model or your virtual source. Now you need to work that out first, and you should have used this formula to work it out. Z0 equals minus 1.02 ds plus 0.083 times QP to the 2/5, where ds is your longest dimension of your source and QP would have been your convective heat output. If you'd have put them in the formula, you'd have got a Z0 of minus 0.66. That's your virtual source, 0.06. Now if you'd have put them in the original formula, the far field model, you'd have got this. M smoke equals 0.071 times 4,500 to the third times 24 minus 0.66. Don't forget 2 minuses make a plus, to the power of 5/3, which would have given you a mass flow rate of smoke of 223 kilograms a second. So we know now how much smoke is being produced. Now we need to know how hot it is. Let's move on to step 4. Step 4 is determining the temperature of the smoke. To determine the temperature of the smoke, the theta value, temperature increase, this is a formula you use. Theta equals QP times M times C, where your theta is your temperature rise, QP is your convective heat output in kilowatts, M is your mass flow rate of smoke, and C is the specific heat capacity of air. Now if you'd have put those known variables in the formula, as you can see here, you'd have got a theta value of 20 degrees Kelvin. That's a 20 degree increase. Now that is just sufficient to maintain buoyancy of the smoke for both natural and mechanical. So you're on the borderline, but it's just enough to maintain that buoyancy. We know the theta value, but now we need to know the absolute temperature, absolute average temperature of the gases. And this is a formula you should have applied. TL equals T0 plus theta, which is your TL is your temperature of ambient air and theta is your temperature increase. This would have given you an absolute average temperature of the smoke of 308 degrees Kelvin. So that's what we needed to know. We need to know the theta value and the absolute temperature of the gases. Don't forget, it's important to remember at this point, if the smoke was over 200 degrees C, it's untenable for life safety. Well, in this case, it's well below that, And like I say, it's still got the buoyancy at 20 degrees, increased theta value. Anything less than 20 degrees, you can't use natural. And in fact, really, you shouldn't be losing mechanical ventilation, unless you've got other factors. 20 is the critical factor. You've just met the 20 degrees, so it does do that. So we know how much smoke we've got and how hot it is. Let's move on to step 5, the stratification check. Now in this case, because the clear layer height is 24 metres, we need to consider the Z max, in other words the stratification point. In other words, we have to work out that it's make sure it's not going to stratify and not make it to the top or make it to the ventilators. That's what you've got to try and work out now, Z max, and this is going to work out whether or not the smoke is likely to make it to the ventilators. This is the formula to apply. Z max equals 5.54 times QP to the quarter times delta T divided by delta Z to the power of minus 3/8, where your Z max is your maximum height the smoke can travel, QP is your convective heat output, delta T is the temperature difference between the top and the bottom of where you're assessing, and delta Z is the height difference between the top and the bottom. Now to do this we need to determine what the temperature difference is between the higher and lower levels. Now let's assume we take temperature readings and identify that the difference between high and low level is 10 degrees. That's what we work out, a delta T of 10 degrees. And your delta Z, we know that's 24 metres. If you put them in the formula here, the Z max formula, you'd have got a Z max of 63.1 metres. So that's the height that the smoke can get to without stratifying. Well, in this case, clearly, stratification is very unlikely to occur. So in this case, you've proven it's not going to stratify, the smoke should make it to the ventilators. So let's move on to step 6 now, which is determining the ventilation requirements. Step 6. Now you've got a couple of choices here. You can go for natural or mechanical ventilation. Now generally natural ventilation is preferred mainly due to cost implications, and that is obviously if it's possible. And in this situation clearly it will be the initial option. Let's progress on the assumption that we're going to do natural ventilation. Now the first thing to determine is the number of reservoirs that you're going to need in your building. So you need to work out how many reservoirs. Now for cost reasons, again, you're normally going to try and have the minimum requirement to meet the appropriate code. Now there are limits to the maximum size you can have for a reservoir. Now the maximum size for natural is 2,000 square metres. Now this can be increased to 3,000 square metres if it's for property protection only. Well in this case clearly it's not. It is a life safety one, so you've got to maintain it at 2,000 square metres. So let's look at our warehouse then. Now we've got our building is 110 metres by 70 metres. Now the maximum size of a reservoir is 2,000 square metres as we've said. So clearly if you divide that out, you need at least 4 reservoirs, minimum 4 reservoirs. So if you break this into 4 now, as you can see, that gives you a reservoir 55 metres by 35 metres. Now the key thing as well is you've satisfied here is you can't have a reservoir more than 60 metres in any direction. And this is to maintain travel distances. The maximum someone's got to travel is 30 metres. Worst case scenario. So 60 metres is another key thing. Well obviously this does not exceed that. So this is okay to have 4 reservoirs 55 metres by 35 metres. Now we need to determine the AVCV factor. We need to work out how much ventilation we need in each reservoir. And this is the formula you apply. Here, this is the AVCV formula. AVCV equals M smoke divided by rho 0. You multiply all that by TL square, which is the temperature of the smoke, plus you've got your AVCV divided by your AICR. This is your ratio, and in this case, as you can see, we've got 4 reservoirs, so 1 will be extracting and 3 will be allowing air in if they're all going to open. So this ratio here will be 1 to 3. 1 out, 3 in. You square that and you times it by TO times TL. You divide the whole lot by times 2, G, which is acceleration due to gravity, times your D, theta, TO, and the whole of that, the square root. This is the formula you apply. Now if you'd have put those in the formula, your variables, you'd have got an AVCV of 89.4 square metres. So we need at least 89.4 square metres of aerodynamic area in each reservoir. So that's what we need. That covers this step. Let's move on now to determine the number of ventilators we need to achieve that. So, we know what total area ventilation is required. Now, this is aerodynamic free area. In other words, you've got to take into account the coefficient of the ventilators, because ventilators are not totally efficient. So, what is the ratio of efficiency? Generally, the coefficient for efficiency is 0.6 for most ventilators. So, if we divide that by 0.6, we need 149 square metres of geometric area from the ventilators. Do you understand? That's what we actually need in geometric area, in physical area. Now don't forget that ventilators don't come bigger than 6.25 metres, and that's because they can't test them any bigger than that. So they don't come bigger than 6.25. So you divide 149 by 6.25, you get approximately, we're going to need at least 24 ventilators. 24 ventilators, that is the absolute minimum that we need in each reservoir. So where do we locate these ventilators then? Where should we put them? Well, before you decide this, you've got to carry out step 8, which is the stagnation check. And what this is saying is ventilators should not be, for natural, should not be more than 10 metres away from an edge, and they shouldn't be more than 20 metres apart. So these are the key rules. You can't put a ventilator more than 10 metres from the edge of a reservoir, or have more than 20 metres in between the actual ventilators. So let's look at our reservoir at 55 metres by 35 metres. What you do is you mark a line at 10 metres and 20 metres. So you mark a grid on it, 10 metres from the edge and 20 metres apart maximum. So no more than 20 metres. So if it's 30 metres in between, you do it in the middle, 15 metres. So make sure there's no line more than 20 metres apart and 10 metres around the edge. And where it intersects, as you can see here, you need a ventilator. So if we were going by the stagnation rule only, we'd need at least, as you can see, we need at least 9 ventilators. That's what we'd need. Now in this case, we know we need 24 anyway. So do you understand? In a way, we need more than what the stagnation rule says. So now we've got to have 24 ventilators somewhere on here. And this is how you do it here. You just spread them out, axisymmetric, all the way around the building, spread it out in the reservoir. So this is what you'd need, 24, and it satisfies the stagnation check as well. So that covers step 8. So we know where we're going to put as ventilators now and how many we need. What you need to do now is work out the plug hole-in check, and this applies to both natural and mechanical ventilation, the plug hole-in check. Now don't forget there's 2 models to determine if plug holing will occur, and this depends on where the ventilator is located. Now the model to use when the ventilator is more than 2 metres from the edge, as is the case we are using now, more than 2 metres, is this formula here. The mcrit equals 2.05 times rho naught times g times t naught theta to the square root times d squared times wv to the half times your TL. Now don't forget in this formula for the plug hole-in check, you've got to work out your WV, your width of your ventilator if it was circular, and this is the formula you need to apply. WV equals 4 times AV per vent, that's the area of vent per vent, divided by pi, divide the whole lot to the square root. Now if you put in your no, we know that the AV required per vent is 6.2. So WV equals 4 times 6.2 divided by 3.142 to the half would have given you a WV of 2.8 metres. So that's what you needed to work out, your WV. Now we've got all the variables, insert them into the plug hole-in formula, it gives you this. You should have got an mcrit of 50.8 kilograms a second. So that's the maximum, based on the parameters you've put in, that can leave each ventilator. 50.8 kilograms a second. So we know that. What you need to do now is make sure that that smoke is not going to leave each ventilator. So what you need to do is work out what your mass flow rate was, which we had earlier, and divide that by the number of ventilators that are extracting. Now our mass flow rate of smoke was 223 kilograms a second. If you divide that out by 24, you've got 9.3 kilograms a second per ventilator. That's how much will be going out. We've got an mcrit much higher than that, so in this case it does satisfy the plug hole-in check. It's very unlikely to plug hole. Let's move on to step 10 now, which is your air inlet velocity. Now in this case, because it's a natural system, you don't actually have to carry out this step. It's only for mechanical systems you have to work this out. With a natural system, you're not going to get the air coming in at such high velocities that it's going to cause problem with means of escape. So in this case, you don't have to work this one out. You can ignore that one. So you can go straight on to step 11, which is your post-design considerations. And in this, you need to work out things like your weather conditions, because if your weather conditions are such that you can't have natural, in other words, if there's a prevailing wind constantly on the top of the roof that you can't actually have natural ventilators, then obviously you need to go for mechanical. And you also need to consider things like tall buildings. If the building is surrounded by a lot taller buildings, you're not going to have the impact of the wind, or it might cause a positive pressure if there's only wind, a tall building on one end. In other words, these are the things you need to carry out now with your step 11, your post-design considerations. And that completes this exercise.